Hi, my name is Amy Guan and I'm from Denton, Texas. For my project, I designed an improved catalyst for methane activation. So methane activation turns methane into methanol, and this is important because methanol is an alternative energy source that has lower emissions and is easy to transport. However, typically methanol production is very difficult because methane is an extremely stable compound. Traditional methane activation catalyst development focuses on modifying the chemical groups directly bound to the active site of the reaction. However, for my STS project, I wanted to gain some new insight into this alternative form of catalyst development, which focused on enhancing the secondary sphere interactions instead. And I did all of this computationally using algorithms that rely on density functional theory. So my first catalyst that I looked at was formate, and this is a standard for all of the later catalysts. And from this formate, I looked at the property values as well as the geometries, and then modified it based on my predictions of what would yield an even lower activation barrier. And this was an iterative process that I used for all of my subsequent catalyst design. And so starting with formate, I added a methylene spacer to enhance the hydrogen bond. And after that, I tested various substituents or various chemical groups. And one of those that I tested was NH2. And looking at this catalyst containing the NH2, I realized that the structure was somewhat reminiscent of that of a dipeptide. And that held a lot of potential because proteins are typically very good at taking advantage of these types of secondary sphere interactions, such as weak hydrogen bonds and dispersion forces. So I mimicked the rest of my catalysts based on protein design. So that would be by adding amide groups or testing different functional groups. And the best catalyst I arrived at from that was this modified and simplified version of a serine dipeptide. And this is actually 10 kcal per mole lower in activation barrier than the formate catalyst was. And this demonstrated that these secondary sphere interactions are a really viable way to improve catalyst development, both in this experiment and in future studies. And looking at this, I wanted to know why certain catalysts perform better than others. So to start off, I looked at the strain versus interaction energy for the catalysts I tested. And there was a negative correlation here, which means that to design better catalysts, it was important to both minimize the strain energy and maximize the magnitude of the interaction energy. So strain energy is the energy required to have the molecules conform to their transition state geometry, and interaction energy is the energy contribution that we get back from the interactions between these different molecules. And next, I looked at the different property values I had. So these included the energies of the molecular orbitals and Lewis acidity and bond length. And looking at this, I created a 8-variable linear regression, and from that I eliminated properties one by one until I arrived at the 2 most impactful properties that influenced the activation barrier, and those 2 were the CH bond length, so that was the carbon from the methane, and then the hydrogen that was being deprotonated, and the bond length of that in its transition state, as well as the OH bond length of the catalyst in its transition state. And I found, based on the coefficients, that increasing the bond lengths of both of these actually led to lower activation barriers. Additionally, looking at the magnitudes of these coefficients, I found that increasing the CH bond length was slightly more impactful than having a longer OH bond length. So from this, I determined this well-performing catalyst as well as some properties to keep in mind for future catalyst design, and these can be used to help further improve catalysts for methane activation so methanol can become a more widely used alternative energy source. Thank you.